All right, y'all, good morning. Today I'm going to show you guys how to use a manipulative to teach simplifying square roots. So this is a lesson that I would use in an Algebra 1 classroom. It actually goes really, really well with one of the tasks from Inspire. So I'm going to try to link that to this video or to the assignment so that you can see kind of how I would use this in the classroom. Um, the objective for students will be to write square roots in simplest radical form. So it's very important that we keep that in mind throughout this lesson because I'm actually going to be talking a little bit about the Pythagorean theorem and area and things like that. So I would make sure that students are um, familiar with those things, kind of talking about the prior knowledge. Maybe putting that in a warm up would be a good idea. You may even want to do your talk about area, talk about area equals side squared and how you could solve for a side by taking square roots. Have that kind of in, go ahead and have students thinking in that way before you introduce these geoboards. You may even want to bring in rational and irrational numbers, just some ideas, some things I thought about as I was planning this lesson, and just know your students and what they might need, refreshing, um, what might needs to be refreshed with them. So keep in mind the objective is to write these square roots in simplest radical form. So that's really where we need to go with this. So I would start by, give me just a minute. Okay. I would start by giving guided notes as well. I would not do this Geoboard activity without some guided notes just for students um, to follow along with. So we're going to do like 5 problems together. And I'd have students draw a sketch of the area model that we do with Geoboards and ask them to write the equation. Sorry about that T there, that typo. I would ask them to write the equation to represent the model as well. So with the area equaling the side squared and have them see that the square root there. Okay. Let's get started. So this is how I would set this up in my classroom. Now, another thing I thought of, I really want them to go from this radical form, radical form that's not in simplest form to simplest form. And I want them to do this without geoboards eventually. The purpose of the geoboard is really just to allow students to see what's going on, maybe give them kind of a visual there and just really, relating the concept of what's happening geometrically as well. So we're not wanting them to model every single radical expression and, with the geoboard and have to have that to convert to simplest form. We honestly want them to be able to do a lot of that in their head. So creating a table like this, I think will help them make that connection as well. So where they can write the radical expression and then the simplest form that we found using the geoboard will really help solidify that and bring those connections together. So we're going to start. So remember, this is what I would give students. We're going to start with finding a side length of a square with area of 9. So here's what I would ask students. I say, okay, so let's create a square and I want it to have 9 blocks inside of it. So I've created that with a yellow rubber band here. So this, I would show students this is going to be, one side. So each of these is like a little block. We're thinking about those as blocks. So we can see that square easily has an area of 9 blocks. So the side length is 3. And so we're relating that to square root. So we're saying, okay, so let's say we'll be able to say that the square root of 9 equals 3. So then we go into 25. So I've got that started here. And students would go, we'll say, okay, well, how can I make a square with 25 blocks? And they'll go, oh, we could do a 5 by 5. It's important that they understand the square, all the side lengths need to be the same. So yes, great job. Okay, so here we are, 25. And so what's the side length of that square? Oh, that's 5, right? Because the square root of 25 is 5. Okay, so let's see. I think I can go right down here to clear everything. All right, so now we're going to start getting into our non-perfect square numbers. And our first one is 8. So students are going to maybe say, oh, we can do a 2 by 4. You know, they're starting to catch on that we're doing these, these factors of the number. And you'll say, oh, okay, so you may draw, a 2 by 4 and say, is this going to make a square? Let's see, 2. Sometimes I mess up. I count the pegs instead of the lines. So and they'll say, oh, no, wait, that's right. And I'll go, well, I can't do that. I can't create a square. And you'll say, well, you can create the square. It just may not be, it may have to be a diagonal. We may have to use Pythagorean theorem here to get that side length. So if you want to make a side length of the square root of 8 is really what we're looking for, right? So we're looking for a side length that gives us the square root of 8 because we want the whole thing to have, 8 squares. We want a square with 8 squares. Then maybe I could, so I was trying to think about taking a square, and I want this square to be 8 blocks in there. We'll say, well, what if we use the Pythagorean theorem? And so we say, I want the side length. Maybe it's like a diagonal, maybe it's not a perfect, a nice, perfect, there it is. I'm wanting to grab this. Maybe it's not on these nice, perfect lines. It's a diagonal. So we'll say, okay, well, if we do the square root of 8, we know that needs to be the square root of an a squared plus b squared. So square root of 8 could be like my hypotenuse. So I need to know what could a and b be. What are two numbers that they need to be perfect square numbers. I can add them up and get this 8. And so you could really guide students here. I feel like as a teacher, you need to remember that this is not the goal for students. We don't want students to make these visuals. Our goal is to move them beyond the visuals. So don't get too bogged down in this. You may say, hey, what if I do a 2 by 2 triangle, and what would this side length be? What would this other side length be here? And then you could get students to do that, 2 squared plus 2 squared, and they'll see that that would be the square root of 8. So you're like, okay, perfect. That's really all that you need here. Your students don't have to be able to create these triangles on their own. Okay, so we'll say, well, there we go. We have one side length of my square. Let's now, let's create a square. So let's keep making these triangles using that Pythagorean theorem idea that if I have, let's see, I'll try to keep these colors the same. So I know that my purple is the square that I'm actually using. Know that, hey, I'm creating a side length of the square root of 8. And so now if all of these, so this is where you're getting students to think here. If this side is the square root of 8 times another side that's the square root of 8, that gives me an area of 8 blocks, which is what I'm looking for, right? I want to know, I'm wanting to model that. Okay, so I have 8 blocks in here within this purple guy. So what I'm going to show students now is where the real learning takes place with simplifying square roots. You're going to say, okay, I want you to look at that square, and can you break up that purple square into smaller squares? And hopefully your students will say, oh yeah, I mean, I could do like, let's see, oh wait, hold on, now I just made 2 rectangles. Well, wait, let's do this. Oh, look, I just made 2 more squares. Or 4 more squares, I'm sorry. So yeah, that's what you're wanting students to see. So then you'll say, okay, so now that you've broken my square with 8 blocks up into 4 smaller squares, how many blocks are in each of those squares? And hopefully they'll be able to do that division really easily. They'll go 8 divided by 4, divided into 4 groups is 2. So each of these blocks has, or each of these squares has 2 blocks in it. So you'll say, okay, well, now give me, so that area is 2. Give me the side length of just that block with an area of 2. And so surely they're getting to the point where they're going, okay, I know the side length is just the square root of the area. So it's the square root of 2, and this side length is the square root of 2. But we also know that side length is the square root of 8 because that's how we created the square, right? It was using the square root of 8. So the square root of 8 equals 2 square roots of 2. And so that's really what we're trying to get students to see. And right, we want them to move from using this Geoboard to just being able to put that on their paper. So we're going to have students write that down in their table and say, all right, let's do another one. Okay. So now I think our next one is the square root of, oh, I'm having to go back to remind myself. The square root of 18. Okay, so we're saying, all right, kids, now we're trying to find a square with 18 blocks is what we want to do. That's our goal. We're thinking of a square with 18 blocks. And they may say 9 and 2, blah, blah, blah. They may go ahead and just know, I can't do that because 18 is not a perfect square. There's not two perfect, nice integer numbers that will multiply, give me 18. So that's all right. Let's use the Pythagorean theorem again. So let's think the square root of 18. Let's think of two numbers that would add to give me 18. And I'm thinking 9 and 9, right? So 3 and 3. So if I have a 3, unclick that or it's going to mess me up here. So I'm going to have a side length of 3. I need to move these guys down here. I just have this feeling that's not going to give me enough room. So I'm going to have 3 by 3. And then that hypotenuse is going to be the square root of 18. And you can check that, tell the kids, hey, do 3 squared plus 3 squared. Do you get, yeah, okay, perfect. So that side length, that green side length, that hypotenuse is going to be the side of my square. And I'm just going to need to create 4 more of those. So you can, of course, you're doing this again with 3 and 3, and then it wants to change the colors on me. That's all right. Okay, so I'm going to go ahead and make this a little bit faster so I'm not taking up so much time here. I say that and then I totally mess up. So here we go. Maybe we're moving on. Let's see if I'm creating a 3 by 3. 1, 2, 3. Yep. Okay. I'm going up 1, 2, 3 and over 1, 2, 3. Perfect. All right. And now you would say, okay, students, so now that we have a square with 18 blocks, how can I break that square maybe into smaller squares? And this is one thing I do love about Geoboards. I've taught this lesson before, but not with Geoboards. It helps students see how to break them into the squares so much easier because it visually, you just want to go ahead and connect more rubber bands here. It's just too perfect to have those pegs across from each other. So students go, oh my gosh, I just made 9 small squares. Exactly. And you'll say, okay, well, how many blocks are in each of those? And they'll divide and say, well, 2 blocks are in each of those small squares. Well, if I know that the side length that I created originally using the Pythagorean theorem was the square root of 18, and now I have 3 side lengths that are the square root of 2. So that is, and you could show them the square root of 2 plus the square root of 2 plus the square root of 2. I definitely would show them that. I am not right now because I'm on a touchpad mouse, and it's just a little hard for me to write all that out, but that's how I definitely would write that out for students. All right, so now you're going to take this, have students put that in their table, and then we can do one more with them. I like this one because it is, I have to click this here. I like the square root of 20 because it's a little bit different. It's not we're not doing a Pythagorean theorem with, a 3 and a 3 or a 2 and a 2 like we were with 8 and 18. For the square root of 20, we can think of maybe 4 plus 16. Those are perfect squares that'll get me to 20. So, and again, I don't want you to get bogged down with that with students. I don't want you to say, oh, my students will never be able to come up with that. Well, that's okay, because that's not the learning goal here. We're not making students create right triangles, giving them the hypotenuse. We're not doing that. So it's okay that they can't come up with that. You doing that for them is fine, because the goal is for them to simplify square roots. So, okay, so like I said, the square root of 20, I could do I said a 4 and a 2. 1, 2, 3, 4 by 2. Let me make sure that makes sense in my head. All right, and so then here's my sine length of my square that is 20. And you're going to do the same thing again. You can already see this guy right here that's going to just be great. All right, so I'm going to go over 1, 2, 3, 4, up 2. Start here. Let's go 1, 2, 3, 4 over 2. I wouldn't skip this step with students, probably, maybe, depending on your students. I'm just trying to not make this video so super long for y'all. All right, so I'm saying again, I've got a square with 20 blocks. How can I break it up, kids? And by this point, they're like, oh, let's break it up into 4 blocks, right? And then you'll go, okay, well, how many blocks are inside each of those 4 blocks? And, again, it's a great visual for division too. I mean, going back to just that simple, what is division? All right, so each of these side lengths is the square root of 5. And so you're saying, well, look, 20, square root of 20 then is just 2 on the square root of 5, or 2 times the square root of 5. And then having kids put that in that table, I think that's going to be a big deal, is this visual table for them. Hopefully they'll be able to see, where the two's coming from, that it's, and you're really wanting to build, you're building this conceptual understanding, but the students are going to take that and hopefully build some procedural fluency based off of that understanding of what that is. One way that I think this would be very powerful is I'm seeing this in Algebra 2 right now. Students are struggling with the 2 times the square root of 5. And how is that different than 2 as an index on the square root of 5? So showing this visual is a perfect way to help them conceptualize what's going on. And so I hope this is helpful. Thank y'all for joining.